Good afternoon, everyone. My name is John Pretz.
Hi, I'm Mana Sahu.
Together, this is Team 11, where we're going to present our project regarding financial sentiment analysis using statistical and NLP approaches. And we're trying to give you an understanding of all the models that we use for this effort and the techniques for the NLP. Slide, please. We're gonna try to give you an overview of what we created, why we did it, and how we went about it. What did we create it for this? We did develop a system for financial news sentiment analysis. Our system analysis sentiment and financial tests for multiple sources, including news articles, social media, and earning calls. Our primary goal was to compare the NLP approaches for the effort, which is included the statistical, neural, and transformer-based models that we use, and to see how they perform in the real world and the financial scenarios. And why did we create it? Because the financial markets are strongly influenced by human emotions, and we're trying to see how the retail investors' sentiment create volatility and event asset bubbles. The social external sentiment also impacts stocks and prices. Understanding this sentiment is critical for the financial analysis. And how do we create this? We implemented three types of NLP models: statistical approach using the TF-IDF, featuring the logistic regression, a neural approach using the BILSTM CNN model, and the transformer-based model using the fine-tuned Feinberg and pre-trained variants. We evaluate all the models using the metrics accuracy, the F1 score, the ROC, UC, AUC, and the confusion metrics showing how the the data was behaving, and also applied the lame explainer to the how to interpret the predictions on the data. Slide, please. On the introduction, we try to make sure that we give you an assessment of how we use the data and how the financial tests, including news articles, social media posts, and earning calls, influence the short-term stock market behavior. Due to the massive volume of financial data, manual sentiment analysis is impractical. The NLP techniques that we use allow us to scale the sentiment extraction from actionable insights. And our goal was to utilize a data record of 1.4 million records and to analyze the data and the company-specific news and associated with stock price. The model output to predict market sentiment and short-term stock prices movement. So this helped to evaluate the data that we have within the sentiment analysis. It gives us an insight how unpredictable the data could work. Slide, please. For the challenges, we trying to figure it out. The data was kind of difficult to uh, rely on sentinel signal from the new social media. So some of the challenges that we have just how to clean up the media with the slang and sarcasm, idiom, and the human language can mislead the models. So we're trying to make sure we clean the data before utilizing for the more models. Like the domain specific jargon complicates the interpretation of the data. So in the imbalanced data set can reduce the performance. That's what the neural model risk overfitting and required computation resources. Capturing the sentiment depth in complex, fine-tuned transformer models is time consuming. So we're trying to use some type of collecting and processing company-specific news and challenging here. So all the models we're trying to help us to identify the levels of the sentiment analysis that we use. Some of the related solutions and the state of the art was the Popola 2024 and Emmett 2023, where we identified the score, the F1 score, the points 87, and for the Emmett 2023, the TF-IDF, it gives us a F1 score of zero point 0.7. For the neural network approach, we find the the use of CNN to extract the local pattern of the byte LSTM give us an F1 score of 0.88 and also 0.85 with the BILSTM model and standing alone. Also, we have other related solutions and that help us out to understand the pattern of the data. Will give us the another neural network approach with the F1 score of 0.81. And for the transformer approach, also we have different models for the GPT-40 and the score that give us an 8.85 and compared to the Feinberg, which is the F1 score of 0.87. So the GPT model have a higher score of the speed of outcome is lower compared to the BERT model. So as you see, the contribution between myself and Manas, we have to show and concentrate more on the baseline database where I find some of the data set that we find out and Manas have other additional data set that we included to have a better understanding how the data will function at a high level scale. So next slide, please. The data collection we use, like I said before, a sample of 1.4 million entries, and we're trying to have a level distribution within the labels that we have. As you see, that's almost identical between the neutral, positive, and negative samples that we have. And we have an observation we notice is a balance scale within the data set that we use. While we processing the data, we trying to make sure that before training the models, we have to clean up the data and make sure that we have some key steps to prior to use the data. We remove the null rows, remove the duplicate data that we have put in the data set that we use, and identify and within the map sentiment labels with the, for example, for the negative, we use the code 0. For the neutral, we use 1, and the positive number 2. And for additional processing, we use the tokenized stats for the models that we use for the BILSTM CNN. As you see on the right side of the screen, show you how the data gets distributed within the map sentiment labels. Additional the methodology that we use for the FSA comparison in stage 1, we trying to use the 3 models here, and then on the stage 1, we split the data set between 80 and 20 training and validation sets, creating a logistic regression model for the TF-IDF and the K-folder cross validation for reliability and robustness within the data sets. So the overall metrics that we use over here, like I said before, the performance, give you the comparison of 500 records within the, 5,000 records within the data sets. And then we use the overall metrics for accuracy and the F1 score and weighted average F1, the ROC and confusion metrics, and sentiment level metrics with precision, recall, and F1 score. And we also have some type of visualization so the group can see how the confusion metrics behave within the levels of the sentiment within the data sets. There's additional, here's the logistic regression model where we identify the the features of 30,000 records used here, and it will show how the confusion metrics behave within the the negative, neutral, positive prediction was giving us an accuracy of 0.9 when and the micro of F1 micro of 0.9047. So basically is giving us a high performance within the data. That's why we're showing on the graphics in comparison between all the models. Slide, please. Here's the BILSTM model, CNN model, where we use the tokenizer with the 10,000 words, and it shows how to behave, and the optimizer goes all the way visualizing all the data that we use, and give us a batch of 64, which is great to evaluate the data sets and with a dimension of 128. So as you see, the total parent is 5 million and converted to 19.63 megabytes. Slide, please. Here's one of the other comparisons that we have where the accuracy shows also 0.92 and shows the confusion metrics for the BILSTM CNN. And Manas, what is the graphics on the left side that you mentioned to that it shows the input layer?
Yeah, so this shows the complete how the input layers are spread across three different types of kernels of CNN and how they're merged, and that output from the CNN model is passed into the BILSTM layer for further processing to create a final output layer.
There you go. So you see the model evaluation that goes to and how the data behave within the process. It's another comparison of the models here, the Feinberg model, where it also has a batch size of 64 and how the data behave within the run and give us the computer metrics where the data seems like it's baseline it to what we're expecting. I will leave you with and ask explain the other graphics.
Thank you, John. So the next slide that we have here is we use three different Feinberg model variants. One for Feinberg meant for sentiment, one meant Feinberg meant for tone of the words that has been spoken, and the Feinberg custom, which is fine-tuned based on the data set that we have. So what we could see is that the performance of the Feinberg, which is meant for sentiment, fails to capture a lot of the actual positive and neutral sentiments, and there's a lot of false negatives and false positives over there. The same is the case that we also observe in case of Feinberg for the tone, where we see which we see a little bit better performance as compared to the Feinberg for sentiment, but still there's a lot of false positives and false negatives available here as well. But when you look at the Feinberg, which we have custom trained for based on the data set, there is a lot of great results that we see, a lot of true positives across all the three sentiment types that could be observed over here. Moving along, continuing on the same three Feinberg comparisons, these are the ROC AUC graphs for the three Feinberg options that we selected and how they perform across the three different sentiments. What you could noticeably see here is that all the three models perform great in case of negative sentiments. So even the Feinberg sentiment or Feinberg tone, they perform good or decent enough for the negative sentiments. Where they fail to perform that well is particularly on the neutral sentiments, which is very close to a random sample. Or like if you just randomizely select anything as neutral, it's kind of that. So the ROCA you see for neutral sentiment is around 0.6 or 0.62, which is pretty close to zero point 0.5. In case of positive as well, it is still decent enough, but still lower than zero point 0.8. So that's what we could see. But when you look at the custom fine but model that we have, this performs exceptionally well across all the three sentiments. And what only proves that if we pre-train a model for our particular data set that we want to measure, it is going to perform well and it is going to give a better result as compared to any pre-trained model. Moving along, some of the other evaluations that we have, this is an evaluation of the negative and neutral and positive sentiments across how each of the different models have predicted it. So here we have tried to keep the true distribution, and then we have tried to keep all the different models over here, logistic regression, bi-LSTM, CN hybrid, and the three different fine but options. So as you could see over here, the logistic regression and the bi-LSTM as well as the custom fine but model, all of them perform quite well across all the three sentiments, almost close to one. And for pre-trained items, for pre-trained fine but for sentiment or pre-trained fine but for tone, they do not perform that well in case of negative sentiments that much. So that is what we could see. Well, also we could see that some of the misclassifications that we see for that are present is primarily on the positive and neutral. So negative sentiments are pretty well captured by these models, but for positive and neutral sentiments, they fail to capture them all the time, and that's where the misclassification could be observed. This is a F1 score comparison across all the different classes for the different model types. So what we could see is that the same thing we can observe here as well. The logistic regression, the bi-LSTM, as well as the custom fine but they all perform close to one across all the three sentiment types. But when you look at the pre-trained items, so fine but like sentiment or tone, they do not perform that well, particularly in case of neutral sentiment, which is pretty close to zero point 0.5 here. And that is what we could see earlier as well in our graphs, and that is what is displayed here in this bar graphs as well for easier visibility. So overall, what you could see is that the a simple model like logistic regression is also able to provide us with good results. And for even better results, we could have a neural network model like bi-LSTM CNN, which has performed well across all the three sentiment categories. So when you look at the accuracy or the ROC AUC or the micro average F1 or the weighted average F1, in all these four cases, these three models have performed quite well. Now, obviously, when you try to fine tune a fine bit model, which takes a lot of computational hours as well as resources, then you're obviously going to get almost perfect results. But in case somebody doesn't have those kind of resources and as well as time, then going for a neural network model like bi-LSTM CNN would do the trick just fine, and it would be much cheaper as well. But something which was surprising to us and which was really great to see is that a simpler model like logistic regression is also able to perform as well as long as the data is perfectly labeled and it has enough time to train on train the model across through multiple k-fold segments. So if it is able to be trained properly, then it is able to detect things better and is able to give the great results as compared to even a neural network or a transformer based models. But when you look at the pre-trained fine-bit models, which have been trained on multiple data sets, they do struggle across all the three segments, three sentiments, because they have not been trained on the exact data set that we used. So this is the complete metrics across the sentiment metrics across all the models. Here you could see the sentiments for negative, neutral, and positive across all the three or for all the five model types that we selected. So that's why you see the 15 um, segments over here. Whereas this is the overall metrics across models, which talks about the accuracy, ROCUC, micro average, and weighted average for all the five models. So you could see the differences here as well. Now, what after we getting into all these different comparisons that we did, we thought that we should also try to see how these models actually perform in a totally different real world example. So the best way to do that is actually put it into into test in real life stock market trends predictions. And that is the part of our stage two of our project. So what we did as part of it is we downloaded all the models that we got. Then we also tried to capture all the historical stock prices. And we also tried to capture different specific news for those companies that we wanted to select. So we chose the Magnificent Seven, the Magnificent Seven stocks, which are Nvidia, Google, Apple, Microsoft, Meta, Tesla, and that those seven items, those seven stocks we selected. We collected the news for all those different companies across multiple days, and we also collected their historical stock prices across those days. That is what we used to feed into the model to so that the model can understand how trends move, and based on that, we try to predict the future stock market trends as well, and try to see how often it is able to match up to that. So we first fed some historical news as well as historical stock prices, then started predicting it and see if it could predict the next day's stock price accurately, the stock price trends accurately or not. So that is the part two of our project. So what we could see here is that these are the preparatory steps over here. This is how we collected the company news about the different seven companies. So we used FinHub's company news API to get the company specific news. We ran the API for the seven companies that I've mentioned over here already. And we cleaned the data of any unwanted columns that is not required for our model to use to keep the overall data collection shorter. Now this data was collated into a Parquet file for better compression. And this is something that we kept on doing over multiple days to make sure that we are always collecting newer data about the company. So every day we would be running the same APIs multiple times to capture newer news data and feed it back into the Parquet file to keep it accumulating the overall news that we get. So and we also made a check that we are not replicating the same news by making sure that any duplicate items are also deleted. This is what you could see the different trends, the news that we captured over multiple days for all the different companies. So here you can see the different bar graphs. In some cases, for some days, some of the companies do not have any news at all, but in some cases, they do have the news. So we try to use all that. Now, how we try to measure the trend? We used Yahoo Finance API to collect the stock prices over different days. And the way we try to capture this is if the price change was more than 0.5%, we used to label it as a positive trend. If the price change was less than 0.5% over the previous day, then we used to label it as a negative trend. If it was between the minus 0.5 to plus 0.5 chart, then we used to label it as neutral. So here you could see a sample of how Apple's prices have moved from the previous day. And if the price change was below zero point 0.5 or within this point minus 0.5 to zero point 0.5 range, we used to keep it as neutral over here. Now we captured the data for multiple days. We ran this data, the different news data across all these five different models. And for each of these, we try to capture the daily sentiment of the company by finding the mode of the sentiment for the news of that day. So within a day, if you have like 10 different news for a particular company, we try to find out what is the majority of the news is about. If the majority of the news is positive, then we consider that the future trend is going to be positive. So that's how we try to capture the future trends. So here you could see that for the different prices, depending on the different news, we have captured what was the actual sentiment. This is the actual sentiment, and then all the different models predictions about the sentiment based on the different news is over here. So some of the observations that we could see here is that, let's say the total number of company and date combinations that we could capture was 67. And for that, we could see that the buy listing CNN was able to accurately predict 50 of those, whereas the Finbert for tone was able to predict the next, which is 32. And thereafter, then the other ones, the other Finbert and the logistic regression were able to predict 30 and 28. So what we could see is that the bialistim CNN neural network performed the best, and the Feinberg tone model performed the best across the Feinberg variants. And it could be that maybe there was a lot of positive stock market trends during that time, and that's why it was able to predict things with a higher accuracy. So again, this is something that could be run on multiple months or multiple months time to actually see much better trends as well. So what we could conclude from here is that not everything needs a transformer-based model for prediction. And even if you have a well-trained neural network, it could provide you with a cheaper and effective alternative. And this is the same observation that we could also see, which was suggested by Cheng as part of the 2025 paper that they published. Additionally, we also try to make sure that we are looking at the overall macroeconomic news as well. So we try to do the same trend analysis for S&P 500 as well. So here we could see the same trend that BioLSTM performed the best along with the Feinberg tone, which performed this equally good as well for that as well. So now after that, we would thought of, well, how about we look at the things which are errored out. Like if a prediction has been positive, but the actual trends were not positive, it were neutral. So why could that be the case? And to understand that, understand the prediction, why the prediction came that way, we used Lime Explainer for that. So here are three examples of the Lime Explainer that we have shown over here. Let's say something was like Blackstone, Jonathan Gray wants AI disruption could upend industries, create huge winners in data and energy, find out why investors are repositioning. If this is the news article all about, because of words like winners, huge, the overall trend prediction was positive by the Feinberg sentiment. But the true sentiment, what actually happened as per the stock prices, was neutral. It did not move more than 0.5%. Similarly, when we look at AI isn't the only reason to buy them, uh, it was the words like buy was seems like it is a positive trend, and that's why Feinberg considered it as a positive trend. But when you look at the actual stock price movement, it was in neutral. It did not move more than 0.5%. Third, this is again another example where words like earnings, reassured, was reassurance was something that was highly positive in nature, and that's why the Feinberg sentiment considered it as positive, but the overall trend of price movement was still neutral. So what we could see is that words like winner, huge, buy, reassurance, all this make the trends seem positive. But as per Greg Basic and Padura in 2023 paper, they showed that sentiments are also a contrarian predictor of stock market returns. And what happens is when market movers see that there's a lot of positive trend, they try to book profits during these times of extreme sentiments, and they get the profits during that time. So while the overall news could be positive, there could be market movers who could sell during that time, and that could bring the price down. So overall, we could see that while the sentiment of news articles gives us some insights about how the future trends of stocks is going to be, that is not the only indicator for an investor. They should be looking at other things like the overall financials and other factors as well. So, what are overall lessons that we learned from this? We understood that fine-tuning a Feinberg model could get us the best results, but the cost of training and computational expenses for that is quite high. So, while it gives us the best results for a specific data set, in terms of real-life examples, we do not see any noticeable benefit over other pre-trained Feinberg models. So, for real-life examples, maybe using the pre-trained ones would be best for people. Now, when we could see is that if we have any attention mask feature, that would be giving us a better results, like in case of summarization and text generation. So for those kind of cases, I think we would think that the Feinberg model would be the best fit for where the attention mask feature is going to be actually useful. But for cases where you're trying to predict a trend or something, maybe other options are better. Now, in cases where you was working on specific cases, maybe neural network models could give us the better results as compared to any costlier transformer-based model. And maybe if the training data is correctly labeled, it is better to go for a bi-LSTM CNN and even a logistical regression as well, which will be much cheaper. So what we could also see is that the fine word models are good at predicting extremes, like extremes in case of positive or negative, but they struggle with the moderate sentiments, whereas neural network models are better at grasping those moderate sentiments. So additionally, what we could also see is that as per Baker and Corridor, the stock market sentiments drive short-term returns. But we could also see that sentiments alone are not a correct predictor of stock market returns. And in some cases, because of market movers' actual actions, the prices could be falling down as well because people could book at in cases where there is a huge positive sentiment going on in the market. So that's why we could conclude that overall, for stock market prediction, company sentiments are not the only predictor. It is one of the predictors, and it could work in multiple cases, but it could also not work for certain times as well, if other market movers actually take a different call. How we could enhance this particular project that we worked on is that what we think is we could also use it for maybe getting into a much better model. Like we use Finebot for feature extraction, but we could use that feature extraction and feed it into a BioLSTM CNN for creating a much more intricate model. We could also use instead of using it as a sentiment analysis, we could also change it to a regression problem as well instead of a classification problem, and that could help us in understanding how positive or how negative things are. So just understanding it as positive or negative sentiment might not be enough. Knowing the scale of positivity or scale of negativity could also be a good add-on in the future. Now, the another thing that we could think of is we could also deploy these models on a real-time data so that it predicts on a real-time price movements rather than on historical price movements, which we currently did. So if somebody expands on this project and makes it much more real-time implementation, that could also be a new add-on to this particular project. And the last thing that we could say is that we currently consider only three sentiment types. So if somebody wants to go into a more fine-grained sentiment analysis, that could also be a new enhancement to this project. And with that, I'll move over to the demo for this. And as part of the demo, I'll go over uh, the different Python notebooks that we used to achieve all this. So the first one I would like to go ahead is the stock accumulation. So let me just move this a little bit easier for me to access. Okay, so the first one is this data accumulation. And as part of this notebook, we captured the data across three different sources. The Kaggle one gave us 4,800 records. The Hugging Face one gave us 1,400,1.4 million records. And the Twitter financial data gave us 12,000 records. And what we did is we started gathering the data, labeled it as per our need, and then we try to clean the data up, remove any duplicates, and then after getting the data from all the sources, we try to combine all of that together. So after we got the data from here, we looked at the data, described it, see if there is any null values or any duplicate values. We did all that. After doing all that, we combined it together, and this is the sentiment that you could see. After making sure that we have removed all the duplicates and null values, we send it back into a Parquet file. This Parquet file forms as a feeder for our next notebook, which is creating a custom find but for sentiment analysis. Now this one, what we did is we took we took a pre-trained find but without the classification head, and after doing getting that, we tried to we got this pre-trained version. We loaded that, and then we created complete uh, a complete data collator over here to keep the overall input to this Finebird model intact. So this helps us in keeping the padded size same. The overall input is going to be same. And as after doing that, we created the overall data set and fed into it. So we created a test data loader and fed into that model, and then we evaluated the model. So what we could see is that across accuracy, precision, recall, and F1 score, it was at around 94% in all the cases. After doing that, we saved the FineBot model, which after we getting it, we went into the uh, third notebook, which is the financial statement analysis across all the five model types. So over here, what we did is we got the data loaded and looked at the different distributions, how well the data have been of different lengths, what is the overall class distribution. We also tried to see how the word cloud for this different data types, like for sentiment analysis of positive, negative, and looked at the overall text length as well to see how many outliers exist. After that, we created k-fold cross-validation for logistic regression, and we used TF-IDF for the features mapping. So over here, after creating the logistic regression, we try to test it out, and this is what we could see after a k-fold of five folds. This is the confusion matrix for that. This is the ROC AUC, which we discussed. As you could see, the for negative, it is almost close to 1, and it is very high for positive and neutral as well. Now, after that, we try to create totally new data set of 5,000 records to measure the performance of different models across it. We also created two data frames, one to capture the model metrics overall for the overall model, and one for a class specific performance as well. So that was something that we did over here. Then we tested this logistics regression model on that 5,000 records and stored it over here. We performed the same thing for BioLSTM as well, BioLSTM CNN. We created the tokenizer, we padded it to 15th, but we looked at the overall sequence length, and then we understood that if we keep a token size of 15, that will cover 95 percentile of our cases. And that's what we did over here to keep every token size same. Now, after creating, this is the place where we create the complete model, wherein we start off with the CNN model. We use three different kernel sizes. And after getting all the kernels, we merge the final CNN output into the BioLSTM layer. So, and then we train it. This is the complete parameter size that you could see here. And this is the overall display of how the complete neural network looks like. So here you can see the three different kernel sizes. They concatenate and then they feed into the bidirectional LSTM layer. Now, we also tested this BioLSTM across the 5,000 test records too. And this is the result that we could see. Here also you could see that it is a great performance overall. And so after testing all of these, we also used to save these models because we were running those models again in stage 2 as well, which I'll cover after this. Then these are the different FineBut models. The first one is for sentiment. We load it and then we test it across the 5,000 records that we talked about in the test data set. And then we record the performance and store it over here. We display the confusion metrics as well as the ROC for this as well. Then this is for FineBut tone as well. We do the same thing. We log the overall metric score as well as the class specific metric score over here, the confusion metrics, and the ROC. Now the final one is the custom FineBut model that we did, and we recorded their overall as well as class specific the scores and the confusion metrics, which you could see is pretty good. There's a very less error scenarios in this case, and that is also displayed in this case of the ROC. So then we compared all the models performances against the true levels as well. So that is what you could see, which we already discussed in our presentation. Now, the next part is the stage 2. And as part of stage 2, what we did is we started off with the news accumulation for this different company specific news. We used FinHub and Yahoo Finance for that to capture the news for, we used the FinHub and capture the news for different, all the seven companies that we mentioned, and combine all of that together. We keep a track of how the news count increases on a day-to-day basis. So that is what you could see. And that is what we use to create this news frequency tracker. So after doing that, we combine all of that into a Parquet file for compressed transportation of the data into the next notebook. So you would have one Parquet file for the company specific news, which is the Magnificent 7 news.parquet, and one for the overall S&P news as well. So this data is then used over here. We upload those two data that the Parquet file that we talked about. Then we also upload all the different models that we have created as part of this FSA comparison notebook, and then we test them out. So this is where we test what is the state sentiment as observed by the logistic regression, what is the sentiment as observed by the BioLSTM CNN, then how the different fine bit models test it out. That also we record it over here. And over here, when you look at the final one, this is what you could see. Then we try to do the analysis, like how often the sentiments are actually matching with how the prices move. So for that, we try to capture the different stock prices over time. So for that, we use Yahoo Finance. We capture the data across different date times, and then find out the actual stock price sentiment based on this hypothesis of ours. So of course, people could choose different brackets for that, but this is the bracket that we chose. And this is how we try to find out how the overall stock price prediction is. So here is the prediction that we talked about. And then this is the model explainer using Lime, where we try to use some of the error examples and try to explain that as well. So yeah, that is what we have for all the different notebooks that we discussed. Moving back to our presentation, these are the different biographical references that we have used. These are the different papers that we looked at, understood how things have worked, and used that knowledge into our project to create this comparison. These are the different research papers as well, and these are the different web sources that we have used throughout this project. These are the different data sets that we used. So I hope you all like what you saw, and that will be all from our side from Team 11 regarding this presentation. Thank you, everyone.
Thanks.